Okay, cool. Thanks, Michael. So thanks for introducing me. It is now my turn to introduce somebody. This is Adam, and you're probably familiar with Adam. You might know him as a grown-up, maybe as the water boy, a golf player, Happy Gilmore, in which he was really good at golf, actually. But to me, Adam is a lot more than that. When I think of Adam, I think of a method for stochastic optimization. And I might mention, before I talk about what that actually is, that Adam Sandler, which is the Adam that you were probably thinking about before, only follows 64 people on Twitter, whereas Adam, the method for stochastic optimization, has been cited more than 220,000 times. So I think it's safe to say that the method for stochastic optimization is more famous than Adam Sandler, more important than Adam Sandler, and more influential. Yeah, Michael?
Number of references in that paper, number of followers.
I crossed that out so you wouldn't see it. So before I talk about what Adam, the method for stochastic optimization is, I should talk about gradient descent first. Because Adam stands for adaptive momentum. It's a type of gradient descent optimizer. And gradient descent is a process for training models. Models themselves take some internal parameters, which we call theta here. That's just how I denote them. And different thetas, so different parameters, produce different performance. The idea behind gradient descent is to repeatedly tweak your parameters in the direction that makes your model performance better until you get good performance from your model. You can sort of cut out the middleman in a way. Different parameter configurations produce different performance. So you can think about a parameter space, the set of all possible parameters, and you can associate each point in parameter space with a model performance. Configurations of model parameters with good performance are regions of parameter space with low values for the objective function or low values of loss. This is how we train models. If our loss landscape or our objective landscape was like a real landscape, like a physical one, then what gradient descent would do is walk down a hill and try and find the bottom of a valley. And it does that by taking one step at a time in the direction of steepest descent. So it looks around, finds the direction of steepest descent, takes one movement, and that represents a tweak to your parameters and a movement through parameter space. Now this is in theory what gradient descent does, but in reality we never actually know what the objective loss landscape looks like. If we did, we just find good regions, find good sets of parameters and choose them from the start. So it's less like walking down a hill and following the contours of some landscape, and more like trying to walk down a hill in the fog when you can see 3 meters in any direction, and you're looking down at your feet, seeing what the gradient's like locally, and following that direction, which is a much harder task. There are a couple of problems that arise when you do this. The first is that you don't know how big your steps should be. If you take small steps, then you don't end up moving fast enough, it's inefficient, but also you can find yourself stuck in like a pothole or something, a very small minima, and the lips of the pothole are too big for you to escape with your small step size. If, on the other hand, your step size is too large and you tweak your parameters too much during every step of the gradient descent process, you might entirely skip over a minima. So you might find a valley that's actually good, but in one step you've completely traversed it. So if your step size is too big, it becomes hard to descend into minima. And if it's too small, you can get stuck in these poor local minima rather than the global minima. What you want is the best region, not just a good region. You don't want to end up at the bottom of like Lake Munga or something where there's the Grand Canyon right next to you. What Adam does is it tells you how big to make your steps. Adam stands for adaptive momentum. It's actually a combination of two different gradient descent optimizers. One called RMS propagation, which was developed by Geoffrey Hinton, and another thing called momentum, which is a separate optimization process in itself. What RMS propagation does is it keeps track of a rolling average of the magnitudes of past gradients, and it bases your step size on the gradients that you've received recently from your previous steps. What I should have said before when I was talking about gradient descent is that you don't just move in the direction of steepest descent, but also by the magnitude of the gradient. You actually follow the gradient vector. So regions that are really steep force you to take large steps, and regions where the gradient is shallow force you to take small steps. What RMS propagation does is it divides by an exponentially moving average of squared gradients. So if you've been receiving large gradient contributions recently in your last few steps, then you're moving through a region of parameter space where the gradient is steep, and you should be taking smaller steps to slow down. If, on the other hand, you've been receiving small contributions from previous gradients, you should take larger steps because you're not moving fast enough. So that's the idea behind RMS propagation, and what momentum does is makes you behave less like a person walking down a hill and more like a ball rolling down a hill. Rather than moving and taking a step in the direction of the gradient vector, you receive a force in the direction of the gradient vector, which changes your momentum, and you move in the direction of your momentum. This can help to smooth the descent process if the loss landscape is bumpy and a bit stochastic locally, and it can also give you enough momentum to escape small minima at times. So a combination of these two processes produces atom, and in loss landscapes that satisfy certain smoothness properties, this is beneficial and better than regular gradient descent. But I would argue that there's something better out there than atom. I think the authors of the paper would also agree. SAM. So SAM stands for sharpness aware minimization, and it's a type of flat minima optimizer. This is a separate class of optimizers. Their goal is to balance performance, so the height in your loss landscape, with the sharpness of the local minima. They prefer regions of your loss landscape that are locally flat than regions that are sharp, right? So like large valleys rather than crevices in your loss landscape. So SAM prevents you from converging in minima that are too narrow in your objective landscape. And the way that it does that is, instead of moving in the direction of steepest descent, it looks around inside an epsilon ball. It looks for a fixed radius, takes a step, finds what the gradient is over there, and then retroactively applies that gradient. So rather than moving at the local gradient vector, you move in the direction of the gradient somewhere else at a fixed radius away from you. Now, if you're in, say, a really sharp minima, and the walls of the landscape are close to you and quite steep, then your epsilon ball overlaps with regions of parameter space where the gradient's really steep, and that forces you to take large steps. So you end up getting kicked out of these sharp minima, whereas if you're inside of a flat minima, like this one, at the bottom of the minima, all around you the gradient is shallow, so you can take small steps and you can converge within those flat minima. Now, there are reasons to assume that flat minima in general, if they're equally good in terms of our objective function, they produce equally good model performance. Flat minima tend to be better than sharp minima. And the reason that they talk about for this, when presenting atom and flat minima optimizers, is that the loss landscape itself is a product of a few things. It's a product of the parameters for our model architecture, and our training data set. When we shift from a training data set to the data set that we would receive in real-world applications of our model, the effective loss landscape shifts and it morphs, kind of like this red line here in this diagram. If we're in a sharp minima and the loss function morphs, so the loss function induced by our real-world data is different to the loss function induced by our training data, then it's like we're close to the walls of the cavern and the cavern shifts, we get forced further uphill. Inside of a flat minima, even if the objective function morphs slightly, we'll probably tend to still be in regions of low loss. What that process is generalization, right? It means that when we receive data that's different to the data we trained it on, our model tends to perform more similarly to the way it did in training. And that's what we want. We want models with good generalization performance, not good performance on training data. But there is another way to think about sharpness, and like another argument you can make for why these flat minima tend to be better than the sharp minima, which is in terms of the minimum description length principle. So I should introduce you to two more people. In black and white is J.J. Rissanen. He wrote about 80 papers on the minimum description length principle, and predating him by several hundred years was a monk, William of Ockham, from the 14th century. But I couldn't find any photos of William of Ockham, so instead I got Microsoft Copilot to create one. William of Ockham was probably not the first person to say what he said, and funnily enough, he didn't even say it in a particularly simple way. But his argument was that the simplest explanation is usually the best explanation. It's quite hard to quantify simplicity or complexity equivalently when we talk about models. So what J.J. Rissanen did is say that instead of looking at complexity and saying that the simplest model is the best model if it produces good performance, then we can look at code length instead. Which model can be described the most succinctly, right? And code length is a good proxy for information content and for model complexity. So he said that the best model is the model that can be described along with the errors that it makes in the shortest possible code. If you could completely describe a model, then you would be able to reproduce the outputs that it creates. And if you also knew the errors that it made, you could add the errors to the outputs and you have the original data set. So you can reconstruct your original data set by encoding a model along with its errors, rather than encoding the data set itself. Now, if you're trying to encode your model errors in binary, for example, then large numbers take more digits. So if your errors are small and the original data points were large numbers, then you're taking fewer binary digits to explain the model errors than you are to explain the original data set. So you've compressed the length of binary text, you've shortened the message, as long as the model itself can also be described succinctly, right? You combine those two encodings and you have a reconstruction of the data set. So to find the best description length, we need to find the cost of encoding the errors that a model makes and the cost of encoding its parameters. Now, there are lots of different forms of the minimum description length principle, and they all take slightly different approaches to encoding the model parameters or the model architecture. But they tend to agree on how we encode the model errors, which is the first term that I've got here. We use a Huffman encoding to encode the model errors, and the length of a Huffman encoding is bounded below by the entropy of the probability distribution that we're encoding, so the probability distribution of the model errors. We assume that model errors are normally distributed, in which case the differential entropy of the normal distribution tells us how much information it requires to encode errors drawn from a normal distribution with a certain variance to within a finite discretization interval. The smaller we make the discretization interval, the more information content it's going to take, because we're specifying our data points more and more precisely. But changing the bin width and discretization interval changes the amount of information content by a fixed margin. And we really only care about comparisons between the information content of different models or different sets of model errors. So the differential entropy of the normal distribution is a good approximation down to some constant shift of how much information content is contained within the errors that a model makes. To describe the model itself, we describe its parameters, and we use self-delimiting floating point numbers for that, which is a bit string, so some string of digits raised to an index power. If we want to specify our parameters really precisely, because we're in some sharp minima, and if we round our parameters, that means perturbing our parameter vector, so changing it slightly in our loss landscape, moving up the walls of the cavern, then we need to include lots of digits in that bit string. So we need to include a long string to denote parameters to which the model is particularly sensitive. If, on the other hand, we're inside some flat minima, we can round our parameter vector, which means shifting through this loss landscape. And that doesn't affect the model errors by much, then we can afford to chop more digits off this bit string and save more code length when we describe the model parameters. So there's a bit of a trade-off between how much we round our parameter vector. When we round our parameter vector, of course, we're moving through this loss landscape, and how much information it takes to describe the model errors. The more variance there is, the greater the entropy, the larger that block of text that describes the model errors. This is definitely true if we're at a local minima, if we're actually at the bottom of one of these basins of attraction in our loss landscape. In that case, any way we move, we make the model performance worse, so we increase the description length of the model errors. But during the gradient descent process, before we reach any minima, we can round our parameter vectors in ways that improve model performance. If we're iteratively tweaking our parameters anyway to move down the slope and find regions of parameter space where model performance is good, then we might as well just round our parameters vaguely in that direction. Right? If one parameter is too big, we can round it down. If another one's too small, we can round it up. In which case, we can save the description length of our model parameters and the description length of our model errors by rounding. When we're inside a local minima, we're at the local minima, there's a trade-off, and we use that to determine the optimal parameter precisions. So how much information we should specify for each parameter. The solution is a quadratic form, and it involves a Hessian matrix here, the second order derivative of the description length of the errors with respect to how much we round our parameters. If that's positive definite, we get a solution. So like we have a quadratic, we have a minimum, so we have an optimal trade-off between parameter precision and description length of errors. But there are situations where if this is not positive definite, there is no optimal trade-off. According to our second order Taylor series approximation of the description length of the errors, the more we round our parameters, the better. So we can't really approximate the description length of a model outside of a local minima by determining some trade-off, some optimal precisions, and this combined code length. What we can do is make a couple of good approximations. We can take a first order approximation of the description length of the errors and the description length of the parameters, in which case, this is f here. The more we round our parameters in the direction of the gradient vector, the better our performance becomes, or at least the better the performance of our approximation becomes. And the more digits we round from our model parameters, so we condense description length in all cases. But we can solve this for a constraint, in which case we're finding the direction that we would want to round our parameters in if we were going to round them by applying a perturbation vector of a fixed size. So we enforce some constraint and say we can only round our parameters by applying a vector of a fixed magnitude, epsilon in this case. That is the optimal direction in which we would want to round our parameters by applying a perturbation vector of fixed size to first order. We can also get a pretty good approximation of how big our rounding parameter or our rounding perturbation vector should be with similar processes to what we use in gradient descent. Finding a rounding perturbation vector, saying how much we would be willing to round our parameters, is a lot like saying how much are we willing to tweak our parameters when we perform gradient descent. In fact, if our loss landscape was replaced with our description length landscape, then rounding our parameters is a lot like performing a step of gradient descent. In which case, any gradient descent optimizer that has some adaptive step size gives us a pretty good idea of how much we can willingly round our parameters. If we're performing small steps because we're near some minima and we're in the fine-tuning process, then we're not willing to round our parameters by much. That means that the information content of the model is high. If, on the other hand, we're willing to take large steps, then the sensitivity to our parameters is probably smaller, and we would be willing to sacrifice more digits of precision when we describe our parameters. So this Lagrangian, which tells us the optimal direction for a fixed rounding perturbation size, gives us a solution in terms of some Lagrange multiplier lambda that implicitly determines step size. So this chi here, this is the rounding perturbation vector, the direction of it for a fixed size. That size is implicitly determined by lambda. I haven't included it here, but when you look at a worst case second order Taylor series approximation, you assume that this first order approximation we made at the start to derive the optimal direction, this has some second order term that we've neglected. At worst, that scales like the leading absolute eigenvalue of the Hessian matrix. The greater the leading absolute eigenvalue of the Hessian, the faster this becomes a bad approximation of our loss landscape, the smaller we're willing to take our step. If we solve for that worst case scenario, we end up with an expression exactly like this, except rather than lambda, we have rho on 2, if rho is the leading eigenvalue. So implicitly, the step size is actually determined by the leading eigenvalue of the Hessian. That gives us a description length across our loss landscape. If we use the synthetic loss landscape that I made up earlier, this is some quadratic pit. This is Rosenbrock's banana function. So this is a flat minima and this is a steep minima, but both with equally good performance in this theoretical case. Then we can assign what the description length of the errors would be if the height of that synthetic loss landscape indicated the mean square error of our model. That's the top left, L of E given theta, so the description length of our model errors across this landscape. Log lambda tells us how big our step size is. Lambda is inversely proportional with the step size chi of lambda. So what this up here says is that inside Rosenbrock's banana function, we have a really high second order derivative. We have a high leading absolute eigenvalue of the Hessian locally. So we're not willing to take very large steps when we round our parameters. We can only round our parameters by a little bit. And that leads us to the complexity. Complexity really just means the description length of the model parameters. And it's much more expensive, according to our MDL calculation, to explain the model parameters inside of Rosenbrock's banana than in that flatter minima, which is the quadratic pit. And when we add the description length of the errors with the description length of the parameters, we get some total description length. Richardson would tell us to try and find the minimum possible description length, which occurs at the bottom of our quadratic pit inside the flatter minima. So our MDL process is telling us that even though the quadratic pit and Rosenbrock's banana function have equally good model performance, we get a shorter description length, so a better model inside the flat minima, the quadratic pit, than inside the sharp minima. And that leads us to TIM. So TIM stands for Training by Information Minimization. Tim is the name of my brother-in-law. Tina is my girlfriend's name, so I was trying to see if I could squeeze an N or an A in there, but I really couldn't. So I'm dedicating this to my brother-in-law, I guess. Chi of lambda was the direction that we would want to round our parameters in if we could apply a rounding perturbation vector of a fixed magnitude. So this is like in what way would we round our parameters if we could round them by a certain amount. This will move us through parameter space the same way that applying a gradient vector would. So what Tim does is it just rounds the parameters over and over again according to this optimal rounding perturbation vector until we get good performance. There are a few things that are kind of interesting about what comes out of this process. If we wanted to round our parameters and we assumed that we were rounding them to infinite precision before we round them at all, then we would need to shave some precision off of every parameter, right? If we didn't round a parameter at all, so we didn't perturb it when we applied that rounding perturbation vector, then we would be expressing that parameter to infinite precision. So Tim tells us that when we round our parameters to achieve the optimal description length, we need to move all parameters by at least a little bit. So Tim forces all of your parameters to change slightly during every step of the optimization process, which is different to gradient descent. So I'm going to show you the performance of Tim, RMS propagation, Adam and Sam on that optimization landscape I made before. I'm going to tell you that Tim is better, but according to Mel Gibson, you should believe half of what you hear or something. So I'll show you instead. On the left here, we have the trajectories of gradient descent for different optimizers in that landscape. Every cross is where we ended up after 30 or so steps of gradient descent using each specific optimizer with different initial locations. So we set initial locations randomly in a grid across this lost landscape, performed some number of gradient descent steps, and ended up at a different location. The black line, these little arrows here, they trace us back to the starting location. So each line and cross is like an arrow, and the arrow head is the cross. That tells us the direction of gradient, or the direction that we moved in throughout our parameter space when using that specific optimizer. An interesting thing to note is that root mean square propagation and Adam really struggle to move through the flat regions of lost landscape away from ether minima, because the gradient vector is so small. Even that compensation that we get from applying the exponentially moving average of past gradients is not enough to force them through this region of the objective function. Sam, interestingly, nothing converges at all within Rosenbrock's banana function, and that's exactly what you want. That's what Sam's designed to do, right? It was designed to send you out of the sharp minima, prevent you from converging within sharp minima, but allow you to converge within flat minima. So Sam does a pretty good job of that. Once you're at epsilon ball, the radius that you're looking around within when you use Sam intersects with the walls of Rosenbrock's banana function. You find some really steep gradient. The radius might intersect the left side of the basin of attraction or the right-hand side of the basin of attraction. And depending on which one, you get flung either to the left or to the right. So Sam sort of flings you away from the sharp minima, which you can see prevents you from converging there, but it doesn't really change the basin of attraction for each minima, which we denote here with the black line, because it just prevents you from converging anywhere. It flings you off to space. You can see Tim moving in diagonal direction through parameter space. This is interesting. It's because Tim forces you to round all your parameters a little bit at least. So when you find the direction of movement, the optimal direction of your rounding perturbation vector, you're looking for a compromise between the direction of the gradient, which is the direction that minimizes the description length of the errors, and a vector of plus or minus ones, where every component is rounded equally, because that's the direction that minimizes the description length of the model parameters, right, where you cut off the most digits. So with Tim, you're essentially you're forced to move in diagonal directions across parameter space until the step size is large enough or the gradient is steep enough to force you to move closer to the direction of the gradient. This means that you can't really converge within Rosenbrock's banana function, and in general, you can't converge within any minima that's narrow enough in one or more directions, because you can't isolate that direction, fix one component and traverse in a direction perpendicular to any coordinate axes. By doing that, you're specifying one of your parameters to infinite precision. And that process forces you out of parts of Rosenbrock's banana function, So it behaves a lot like a flat minima optimizer, Tim, which is not, I guess, super surprising because, again, we're preferencing the flat minima to the sharp minima when we're looking at description length in general. On the right, we have the same sets of graphs, but all of these use Tim with different values of mu, and mu is a hyperparameter that transforms us from traditional gradient descent to Tim. It changes the weighting that we place on the description length of the model parameters compared to the description length of the model errors. When mu is 0, we don't care at all about the description length of the model parameters, so we just move in the direction of the gradient vector. When mu is 1, they're equally weighted and we're using Tim. And in these diagrams, I'm using the same step size for all values of mu, whether we're using traditional gradient descent for mu equals 0 or Tim when mu equals 1. This is to show that what's changing the basins of attraction for Tim is not just step size. If you take large enough steps, you're not going to be able to converge in anything. And so that would prevent you from converging within Rosenbrock's banana function. But even when we take equally sized steps of Tim compared to traditional gradient descent, the basins of attraction change. We can converge inside of Rosenbrock's banana function when mu is 0 and we're using traditional gradient descent, but not when we're using Tim. And that's because when we use traditional gradient descent, you can move downwards along Rosenbrock's banana function. This is all well and good, I guess, but these are synthetic objective functions that I made up myself. They don't represent any model at all. So probably a better test to see if Tim's actually useful is to take a real world model, train it with either Tim or traditional gradient descent, and see if there's any advantage for using Tim. So a recurrent neural network is like a combination of an echo state network and a feed-forward neural network, except that we're training every possible edge and every possible bias in this network. So every node here has an associated bias term, and every weight is a trainable parameter. So we train all the weights and all the biases in every layer of this recurrent neural network using either gradient descent or Tim for the purpose of predicting a few different time series. So we have the Chen equations, the Hannon-Hiles system, and then the Mackey-Glass system from top to bottom. These are dynamical systems that are chaotic. The further you predict ahead, the more difficult it becomes. And we use either Tim, mu equals 1, or traditional gradient descent, mu equals 0, to train that recurrent neural network for some different number of training epochs. One training epoch is once you've cycled through all of your training data once. And we look at the performance after a given number of training epochs in every case. And we find in general that for the same number of training epochs, recurrent neural networks trained using Tim, in this case at least, are performing better than those trained using traditional gradient descent. To try and make this a fair comparison, because generally it's quite hard to compare between different optimizers, they're all suited for different tasks, we're forcing the step size to be the same. We used a process here where we fixed a step size of 0.1 or something for the first step, and then if performance on our training data gets worse, we halve our step size. If performance gets better, we multiply it by 1.2 or 1.3, so we increase our step size slightly. And where we're solving that lambda, the Lagrange multiplier, to implicitly determine a step size for Tim, so that the step size is equivalent in all cases. And we're trying to just isolate the direction of movement for Tim compared to gradient descent. There is an explanation for why Tim performs better than traditional gradient descent in this case. First of all, we can look at which parts of the network are being focused on by different optimizers. These are the different layers in our recurrent neural network, and what we're plotting here is the average change made to components within each layer. The green lines here, traditional gradient descent, are really focusing on the output layers. So changing the output parameters a lot and not really changing omega rec here at all. Omega rec are the recurrent internal weights. These are like the internal connections of our echo state network. Instead, traditional gradient descent focuses on these layers, so these weights and biases out here. There's something called the vanishing gradient problem in recurrent neural networks, which is a bit of a catch-22. Your echo state network, this recurrent layer, performs a mapping that's a lot like a time delay embedding of previous time series inputs. And it has some memory capacity associated with it. It has some recollection of what you fed into it last time step, a little bit less recollection of what you fed in the time step before, and so on, until after some long time lag, it's forgotten almost completely what the time series was that long ago. Now, when we train with gradient descent, we're training the feed-forward layers of our network to predict the next input based on the state that they can observe from the echo state network, or the recurrent part of our neural network. And if that recurrent part has no information of long time lags, because there's small memory capacity in our echo state network, then there's no reason for them to change their weights in a way that uses information from long time lags, so they don't really have access to it. So the output layers don't care much about long time lags, which means there's no incentive for the recurrent connections to change in ways that increase memory capacity and give them access to the time lags that they don't really care about. There's this catch-22, which is called the vanishing gradient problem. Because TIM forces the recurrent connections to change slightly in one way or another, they might as well change in the way that improves memory capacity, even if this is only slightly beneficial and not something that traditional gradient descent would really care about. So we find that when we isolate the recurrent component of our neural network and look at the memory capacity after some number of training epochs with different optimizers, that we get much better memory capacity when we use TIM than when we use traditional gradient descent, because traditional gradient descent, that vanishing gradient problem occurs and we don't really change the recurrent connections at all. So I think this vanishing gradient problem partly explains why TIM is outperforming traditional gradient descent here, at least. This is a specific case. This is a problem that occurs in time series modeling, not in, say, image prediction or something like that, image classification. But I think it's a good illustration that if you want to try and compensate between different components of some neural network, then there might be an advantage to using TIM, or there are at least cases where TIM is advantageous and preferable to traditional gradient descent. It also comes with that model selection criteria attached. Along with TIM, you get the minimum description length of your network for free, which is some method for choosing your neural network, right? Rather than just looking at how well they perform on training data, which might be a bit misleading when you use real world data. You can look at the minimum description length network that sort of comes with TIM for free. Anyway, that concludes my talk. If anyone has any questions. That is.
Yeah, that was the last slide.
Oh, yeah.
Ask.
God.
Any questions?
Yeah.
Can you go back to when you were comparing different values of mu in those plots? Sorry, you compared values of mu for everything. On the banana function plot.
Oh, yeah.
Why exactly is there like this horizontal vertical biasing around that flat?
As in why are they coming in from these directions? What's happening is it's jittering diagonally back and forward until it gets to a part where there is zero gradient in a given direction. When you choose the direction that you're moving in, you're trying to compensate between the gradient vector and some random plus or minus 1 vector. And you would choose the quadrant of that plus or minus 1 vector that's the closest to your gradient vector. So if your gradient vector is pointing this way, any vector of equally weighted components is good for decreasing the description length of your parameters, but you would choose the one that's close to the vector, the gradient vector of your loss landscape. If the gradient vector of your loss landscape has a 0 in one of the components, then rather than randomly deciding a direction, I think I just ignored it. So it ends up getting to a point where it doesn't move in diagonal directions. It just ignores a component and forces you directly downwards. I could change that, and that might be better, and add a bit of like stochasticity to the process.
So it's the case that it's traveling 45 degrees plus or minus,
Yeah.
and it's going downhill all the time until it gets to the vertical horizontal.
Yeah.
When if it continues traveling 45 degrees, it's going to be going uphill in one direction or the other. So it then starts tacking backwards and forwards.
Yeah, well, yeah, so essentially it can't determine whether it's better to go in that 45-degree angle or that 45-degree angle, so it just goes that way.
Also, it does actually go straight, it doesn't just flip.
Yeah, you could do either. You could get it to randomly pick, in which case it's going to zigzag. That's probably better, actually, than just, because otherwise you lose the whole process that forces you along a diagonal. But
I'm going to ask about this as well, because it looks like you can blur your eyes and see where the red dots are going to be without having to do search space computation.
yes, yeah. Yeah, I mean, so this is an example where I completely made up this loss landscape.
But does it make sense to not have to do any of that fine tuning? Like, am I interpreting it wrong? Can I just, see that these lines are going to intersect, and this is where my red will therefore be?
Yeah. So you could do that for sure, but what that would require you to do is take several steps of gradient descent from a bunch of different locations, right? So you would take lots of different points and essentially see what the flow is like across your parameter space. That's more and more expensive the higher the dimension of your model. So in a 2D cross section, you can get a 20 by 20 grid. For a 3-dimensional model, you need a 20 by 20 by 20 grid, and so on. So when you get really high dimensional models, although it's probably a lot better to initialize lots of models randomly and see where they all end up, then you're less likely to get stuck in some small local minima. It just becomes too computationally expensive. So we pick one random direction. We would pick any of these points randomly and just follow it, rather than seeing what the flow is like across our loss surface.
You showed us lots of different information criteria, description lengths at the beginning. How sensitive are these results to choosing a different description length? If you can, use the Schwartz criterion, which is probably about the simplest, versus one of the fancier ones that involves some optimization, does it make much difference for these?
I'm not really sure. I haven't looked into that at all. I was definitely thinking that, because right now I'm basing everything off numerical data. So we're predicting a time series. We can look at assume that our models are normally distributed, at least, like the errors are normally distributed. If we had some image classification problem, then our loss function would be like a cross entropy or something, and the information content of our models would be a bit different, or the information content of the errors would be different. For the description length of the model parameters, we're looking at that floating point encoding. There are other ways we could do it. We could assume some prior distribution over the parameters. That's what Geoffrey Hinton did. He assumed that your model parameters were sampled from a combination of 5 different Gaussians. So we created some Gaussian mixed distribution as a prior, and then looked at the Gould-Beck-Leibler divergence between his prior distribution and his posterior distribution after training the model. And that was the information content of the model parameters. But I think that becomes really hard then to, like, I don't think you would be able to base a direction, like a gradient descent optimizer off of that process. It possibly you'll be looking at directions that reduce cross entropy between some prior and posterior distribution. Yeah, but there are. I mean, the way that the most common form of MDL now is like the stochastic complexity stuff, which is real hairy, where you're integrating over all possible data sets or something, looking at the maximum likelihood estimate that comes out of any given data set. Yeah. Zara? Or here and over here?
No, just the right bottom quarter of the circle shape of the flat minimum. Can you zoom in on the picture?
Possibly. Whoa. This one? So over here,
Yeah.
do you mean?
Or do you mean in the fourth quadrant? Because there's points that converging more slowly in the fourth quadrant than the second quadrant.
Or here they're struggling, you mean?
No, no.
In between the banana and the circle.
Or here? Yeah. Okay, yeah. So I think it's struggling a little bit there because it's trying to pick a diagonal direction to move in, and there's probably a very slight difference between which diagonal is best. So if it's slightly closer to the circle, it's going to want to move like diagonally this way or this way. If it's closer to the banana function, it's going to want to move in a diagonal like towards the banana function. And here the loss landscape looks flat, but there's sort of slight variations in it. It's like very slightly angled in different ways, and that changes where you're taking a step completely. So Tim will force you to still take a big step in one diagonal or another. And based on some tiny fluctuations of your gradient there, you're sort of almost randomly picking which direction. Or you're looking at some concavity landscape here that might be quite complex, and we just can't really observe it because it's all roughly the same height. There's like a big problem here. So the basins of attraction are doing something odd in this region of parameter space as well. I don't really know what the concavity looks like there, but I'm assuming there's some interesting change of slope going on that's giving all of the optimizers a bit of difficulty in that region as well.
When you are doing the rounding of your parameters, you round and then you move again and it potentially grows again and it's doing this breathing in and out, or is it always certain bits and reducing?
Yes, so yeah, I say that we're rounding parameters, but when we try and balance the description length of the errors with the description length of the parameters, I mean, really, there are only finitely many ways you can round your parameter vector by applying a perturbation, right? Like if you had a parameter that was 1.56, you could add 0.04, you could subtract 0.06, but you couldn't add 0.03 or something. Will we take a continuous approximation? We assume that when you round your parameters, you're perturbing them by some vector, and we solve in Rn, we solve for real value components, and we assume that there exists a difference between the rounded parameters and the parameters to full precision that's close enough to that vector. So we're not actually, otherwise we'd have like a very difficult problem where we're looking for a bunch of discrete, like a finite number of possible roundings. And yeah, every time we rounded our parameters, we'd shave more information off them. And once they'd been rounded to the nearest 10 bits of precision, we couldn't, again, round them from infinity back to 10 or something. So
It's that assumption that's letting you be so strict about rounding at every moment.
yes, yeah. So it's really like, it's not so much we find the optimal rounding vector. It's like, if we wanted to round our parameters by moving them in some direction, we would want it to be like roughly in this direction. And there probably exists some actual difference between a genuine rounded set of parameters and our parameters to full precision that's close enough to that vector. But instead of figuring that out and actually rounding our parameters, when we're looking for the information content, we're just like, the more we can round it, the more precision we can shave off in general. So the bigger the step we can take, the more we can round our parameters. Otherwise, if our parameter was really, really close to like an integer or something, our description length would be very different to if it wasn't. Yeah, so we're like, we'll round them, but we don't actually round them. And then at every step in the process, we're back to square one. We don't actually ever have a rounded set of parameters. Yeah. What we would do to find the actual rounded set of parameters that we want is we would find some direction, vaguely, where our error gets smaller, and we look for some genuine rounding vector in that rough direction. So we can look at how much we'd be willing to round each parameter, and then sort of take like the ceiling of that, or the floor of that, and round them by the smallest power of e that's less than or equal to that amount. So if we were willing to round our parameter by up to 0.9 or 0.09, and its value was 1.56, we'd say, okay, and we wanted to round it down, we'd say, okay, we round it by 0.06. And from there, we determine the actual rounding perturbations. And that's good for calculating description length. But during the gradient descent process, we can just leave it like that. Apply the exact direction that we would hope